The wound rotor induction motor. The construction of the wound rotor is very similar to the squirrel cage induction motor. They have the same stator design, same end bells, same bearings. Cooling methods are very similar, and the enclosure designations are the same. Difference is the rotor and the rotor circuit for the wound rotor. The rotor has windings, not bars, and these windings are connected to slip rings. At the bottom here we have some brushes, and they're contacting slip rings. They're down here. On the upper right here, we can see a wound rotor here with the 3 slip rings on it. And then again here on the far right is just a diagram showing what the brush holders look like. The rotor is constructed by winding 3 separate coils on the rotor 120 degrees apart and star connecting them internally. The rotor circuit is then brought out through some slip rings and brushes to some external resistances. Now these lines that are brought out we identify as M1, M2, and M3. The rotor circuit is referred to as the secondary circuit and is mentioned in section 28 of the Canadian Electrical Code. So the primary circuit is the stator circuit, the secondary circuit is the wound rotor and the rotor circuit. External resistances can be fixed or variable. Okay, shown here on the right is a fixed resistance bank and a diagram on how they're going to be connected to the rotor circuit. Here we see the M1, M2, and the M3. They're going to be connected out to an array of resistances. The contacts spanning the different sections of resistances are the bypass contactors. So we can stage the amount of resistance that's going to be taken out of the circuit. Okay. And this schematic here is showing fixed resistances. And then again, T1 and T2 and T3, that's the designation we give for stator connections. I'm going to get into the connection methods a little later on. This is what a variable resistor controller would look like. So up on the right is a lab variable resistant controller. You turn the dial and it's going to sweep across to the various amounts of resistances. And then we can see down here below, this is what the schematic would look like for that same switch, where it's going to connect. Top line here is going to go to M1. This next one's to M2 and then to M3. So as you can see, the resistors here are a Y connected, and they're going to be Y connected to the Y connected rotor circuit. The wound rotor induction motor operates very similar to the squirrel cage, where we have a rotating magnetic field, synchronous speed, and an induced rotor voltage are all the same. The difference is how the rotor current is controlled. So the wound rotor induction motor has several advantages over the squirrel cage. The wound rotor induction motor, it develops the highest starting torque per amp of starting current of any of the three-phase motors. Okay, so it requires, to have a really high amount of torque, it requires not as much starting current. And the torque in the wound rotor induction motor is variable. So we can control that by controlling the amount of current going through the rotor circuit by increasing and decreasing the resistance in the rotor circuit. Okay, and the amount of starting current for the same reason can be controlled. We control the amount of current in the rotor circuit. It's going to control the amount of current that's getting put through the stator circuit. So we can control that starting current pretty well. Okay, the motor speed can be controlled. We can add and take away resistance in the rotor circuit, and it's going to change the torque setting. So if we want to slow the motor down, we can add resistance into the circuit. If we want to speed it up, we can take resistance away. Acceleration can be very smooth. We can put several stages in fixed resistant type of wound rotor motors, so we can slowly and gradually have a nice smooth ramp or an acceleration for the motor from no speed to full speed. The power factor for the rotor can be controlled by adding resistance to the rotor circuit wall. That's the main thing about the wound rotor motor is we're adding resistance and taking resistance away in the rotor circuit and manipulating the power factor. And the stator winding, it can also avoid overheating caused by high sustained inrush currents. Okay, so we can, during startup, we can control the rotor current, which controls the stator current. So we can really control and limit the amount of inrush current that the stator windings are get subjected to. All are accomplished by controlling the rotor resistance. Some disadvantages, though, with this wound rotor. It's an old technology. They're not used too often anymore. They're large physical size. They're probably about 25 to 30% bigger than the comparable squirrel cage motor. High initial cost. There's more windings. There's more for manufacturing wound rotor motors. It costs a lot more to make one of those motors, so the initial cost is going to be higher. Plus, the materials that the wound rotor motors made of, there's a lot more to it. So the initial cost for purchasing will be high. Higher maintenance costs. Anytime you have slip rings or brushes, your maintenance cost is going to be quite high. More complex controls. Relative to what the motor's doing, to control it, you're getting all extra contactors, and in the power circuit, you're bringing extra components in there that aren't necessarily necessary anymore. And it has it can get poor speed regulation. Okay, if you leave the resistance, or if resistances are left in the rotor circuit and you add load, it'll really have a poor speed regulation. So you guys may have remembered this graph from one of the earlier videos. This is a graph showing, get my laser out, the torque curve for a type A or a type B squirrel cage rotor. Now, if you look at the curve, they all have, and the other rotor types have the same characteristic, where they have a peak torque at always 25% slip. So I'm down here, 25% slip is where our peak torque is going to happen. Now, another interesting thing that happens with these guys is they peak their torque always at 70% power factor. Okay, so that's good to know. We can take advantage of that, and that's the rotor power factor. So 70% power factor is about 45 degrees. Okay. So here we have the torque profiles for 4 of the rotor designs, for the squirrel cage rotors. And you can notice at 25% slip, all of them pretty close to, they all should line up with their maximum torque should be at 25% slip, and the power factor for each of them will be at 70% for their maximum torque. So this concept we can take advantage of with this wound rotor motor. We'll get into it in a second. First, let's kind of review rotor power factor. So our rotor power factor is proportional to our frequency. So as our rotor accelerates, our frequency goes down, and our power factor angle is gonna get less. Okay. So what the wound rotor motor is doing is we add resistance into the rotor circuit, okay, to try to manipulate the power factor angle of the rotor. Okay, now in those previous slides we saw that 70%, 45 degrees, 70% power factor gives us the highest torque out of all the different types of rotors, and that holds true with the wound rotor. When our squirrel cage induction motors and our wound rotor motors are at 70% power factor, rotor power factor, they have their highest available torque at that point. They'll be able to generate their highest amount of torque. So what we do is, if over here we look on the side, this triangle, the smaller triangle with the phase angle A, that's what a squirrel cage induction motor power triangle power factor would look like at startup. And then as it accelerated, our XL would decrease. Okay, so, and it would slowly make our power factor angle smaller. But with the wound rotor, we add resistance into that circuit, so we can again make our power factor angle smaller here. Okay, now the ideal amount is going to be, this angle is going to be 45 degrees. So what that means is our resistance and our reactance are going to be equal. So if we can keep those equal, we're going to have the highest amount of torque that we can get out of these motors. Okay, so what we can conclude here is, if we increase our rotor resistance, our rotor power factor angle will go down. Okay, which it did. We increased the resistance here. We made this angle B here is going to be smaller than angle A, and that will in turn make our torque go up. So if we look back at this graph and see that that at the highest amount of torque for this particular rotor is always going to be at 70% power factor, we can conclude that if we can have our rotor power factor stay at 70%, we'll be able to maintain peak torque for the operation of the motor. Now, if we look at this graph here, what it is it's the torque profile for a wound rotor motor with the resistances shorted out of the rotor circuit. So in essence, it's connected exactly like a squirrel cage motor would be. The big problem is there's quite a bit of power factor in with regards to the windings there. So, and there's some high resistance in those windings themselves. So we're going to have a pretty low starting torque. Okay. And then it's going to slowly accelerate until it hits 70% power factor for the rotor. So right now, this is what it would look like something at startup. We're going to have a very poor angle here. But then it's going to slowly, as it accelerates, our XL's reducing, okay, until we get to this, the power factor angle goes to 45 degrees, and then the XL is going to be, the other angle is going to be 45 degrees, and our resistance will equal our reactance. That's going to be at this 25% slip. Hey guys, our next graph here is showing, let's see if I can get laser pointer to work. Laser pointer's not helping me. It's a little glitchy right now. So this graph shows what the torque versus slip will be when we remove half of our starting resistance from the secondary circuit. So that would be our XL is going to be twice as high a value as our R. So our power factor is going to be a lot worse, okay, at that point, and our torque is going to be a lot worse at startup. So what we see at the beginning, right, first the dotted line above it where it says full resistance, that's what the torque profile would look like if we had at startup the optimal amount of starting resistance. Okay, so at that point XL equals R, but we're starting at 50%. So at 50% resistance, our torque isn't going to be optimal amount of torque. It's going to be a little bit lower. Okay, so the motor, it's going to start accelerating. Our torque's not going to be as high as it could be as for startup, until the frequency in the rotor reduces as we accelerate, and that will reduce our XL until it gets to a point where the XL's been reduced to a point where it equals our R, and that's at 50% slip, and 50% slip is going to be 60 hertz rotor frequency. So it's going to eventually hit the optimal amount of torque at 50% now, and then it's just going to drop off. If we don't start taking more resistance out of the circuit, eventually we're going to have such a higher amount of induced voltage, or sorry, a low amount of induced voltage, where we're not going to have enough current to maintain rotor flux. And then it's going to drop off, and it'll eventually lose a lot of torque and could stall. So right here at that 50% slip, our rotor power factor will be 70%. Now if we have a look at 100% slip, where we size at 100% slip, our R, our resistance, is going to equal our inductive reactance. Our power factor will be at that point. Okay, so 100% slip, our power factor will be 70% at that point. Now, that's good. Problem we have, though, is as we accelerate, our power factor is going to reduce, and that's not good either. Okay, it's our torque is going to start to drop off until we can increase, because our resistance in our rotor circuit's too high. So we're not inducing, well, we're increasing induced voltage, but the current isn't going up proportionally because we have too much resistance in the circuit. So our torque is dropping off because we have too much resistance in the rotor circuit at that time. So that's why we stage resistors in this wound rotor starting circuit. So this is what different stages of resistance would look like in our wound rotor circuit. We have our A is without any resistance. Our B would be with 50% resistance in our rotor circuit, and our C would be at 100% at startup, okay, in our circuit there. Here we have a wound rotor circuit where we have our motor with our stator leads coming in, and we have our secondary circuit here with some resistors and some bypass contactors here. So how this works is this is a 4-step or 4-stage starting. The first step is going to be our stator gets energized. So we're going to have our main contactors are going to close. It's going to energize the rotating magnetic field in our stator, and that's going to induce voltage into our rotor circuit now. Now we have induced voltage in our rotor circuit, and we have resistance in our rotor circuit. So we're going to start having current to flow. Now the current flowing through our rotor circuit is going to be limited by these resistors. So our inrush current is going to be pretty low because these resistors are limiting that current. Okay, now we're going to go through some steps on how this works. Okay, now this is the graph profiling the operation of that previous schematic we were just looking at, that 4-stage or 4-step starter. So first step, what happens is the stator contacts close. And what that does is it starts our rotating stator field. Okay, and now our induced voltage in our rotor circuit is getting generated. It's to its maximum voltage, but we have resistances. We got 3 sets of resistances in our rotor circuit. So our power factor angle should be at 45 degrees. Our power factor should be 70% at this point. Now, that means our torque is going to be at its potential maximum here. So this looks like it's about 125%. This should probably line up with 100% slip. So as our wound rotor motor accelerates, okay, we're losing power factor. Okay, our frequency is reducing and our XL and our rotor is dropping. Okay, so what's left now is we have a high resistance in our rotor circuit. We have reducing voltage now also in our rotor circuit. So our current in our rotor circuit is not increasing enough to maintain torque. It's eventually just going to drop right off. So we take another set of resistors out. Bang! We close A. It bypasses the first set of resistors. All of a sudden we have a big increase in current in our rotor circuit. Okay, and now that's going to jump us up to, looks like about 175% torque. Now the motor's going to keep accelerating, and again our XL is going to be reducing here, and our induced voltage is getting reduced here also. So with our reduced voltage, we're losing current. So eventually we're going to drop down to this point, and this is a predetermined point where we're going to have B contactor close, which is going to bypass the next set of resistances in the rotor circuit. Then we're going to have a big jump in current because now we have the voltages high enough to get a decent amount of current at that resistance, Ohm's law. Okay, then we're up to 200% torque. Okay, now these steps are, depends what the application is. They're not all going to be like this. So now we're at 200% torque, and our motor is, again, it's the induced voltage in the rotor circuit is getting less and less as we accelerate, and our current proportionally is dropping as we accelerate until we get to this next point where we close our last contactor and bypass the remaining resistance. When that happens, we can have a small jumping in rotor torque or in motor torque, and then it's slowly going to come down. So now this is with no resistance in the rotor circuit, and it's going to start behaving very similar to a squirrel cage motor. Here we have a three-stage wound rotor motor circuit here, where the first stage will be, well, when we energize our stator and start our rotating magnetic field. That's going to, and as we looked at in the previous slides, that's going to start and induce voltage into our rotor circuit. We're going to have current flowing through our resistors, and then we stage out each set of resistors. Just to kind of review, the T1, T2, T3 terminal identifications for stator terminals. We also have a couple more designations when I get into motor connections. We're going to look at all those different numbers and connections and conventions. Right now we have our M1 and M2 and M3. Those are the lead designations for our secondary circuit here. Okay. Now when we're looking at that three-stage contactor, at the beginning, this is actually, I find this graph's a little more intuitive than the last one we were looking at. We energize the motor. It's got all the resistance in the circuit. The resistance at this point, is going to equal the inductive reactance at this point. Now, as you know, as the motor increases speed, our inductive reactance is going to drop. So if we do not adjust our resistance to compensate for that, we're going to eventually, it's going to drop right off, and we're losing our optimal torque. So at this point here, at 75%, we disconnect the first chunk of resistances out there. That causes another torque increase here when we have only a contactor closed, and then eventually we're gonna it's gonna drop down again, and then we're gonna close B. So on the next slide, here we have the wound rotor motor circuit at stage 2. So right now the stator contactors are closed, and we have our rotor starting to turn. We have all resistance in the circuit still at this point. Okay. Then, as the previous graph we looked at, our current in our rotor circuit, it's going to start dropping off because our voltage, our induced voltage, is dropping down. Okay, so that's at A and B here. So it's going to start up, we're going to have maximum torque, and then eventually it's going to start losing torque. So we close the first set of contactors, and then also the motor is accelerating at this time. Okay, now we have one set of resistors in there, which is this point here. So it's going to still have a decent amount of torque while it's still accelerating until it gets to this point here. It'll still accelerate, but it's going to lose torque. So if there's any load on the motor, it's going to cause the motor to slow down and not accelerate. So now we have our last set of resistances taken out of the circuit. Motor's going to be going full speed, and it's running as required. I hope that was enough one rotor motors for you. Thank you very much.